well, okay, how many categories do we want? Let's do 100. So she disappeared. She came back 2 months later with 101 categories. And that became Caltech 101.
Welcome to Inside ALLSIDES. This is our second episode. And for those of you who are new to this podcast, we try to cover many things around the topics of 3D AI, and physical intelligence as well, but most so interested in computer vision and machine learning topics. And we have the privilege to talk to many people who contributed to this space, from the research side, scientists, professors, and as well as investors and entrepreneurs. And especially today, I'm very, very excited, and not to say emotional, to welcome Professor Pietro Perona to this podcast. He has been a friend for quite some years right now, and we came to him asking for advice and a bit of guidance as we were embarking on our research story first and then entrepreneur story. And for those of you who don't know, one of the pioneers in this field, I'll just quickly introduce the major highlights. But then, of course, would love to hear in his own words what he has to say. Welcome, Pietro. First of all, it's a pleasure to have you.
Welcome, Pietro.
I'm glad to be here. Very good to see you.
Professor of Electrical Engineering and of Computational Neural Systems at the California Institute of Technology. I think you have been teaching there for 2 decades almost, or a bit more even. Lots of teams that work on computational foundations in vision. And also you're an Amazon fellow, bringing AI to the cloud. But one thing I will say, and everyone can agree on, surely a pioneer in this very, very exciting space of research. And I would love to maybe say it a bit in your own words. In the early days, what were you working on, and what was some of your focus areas that led you to this point here?
So, Franz and Burkhard, thank you for inviting me to your podcast. And it's lovely to be here with you for a little bit, talking about computer vision, which is, of course, my passion. So my story starts, let's say, even 40 years ago, because I started being interested in computer vision in 85, 86. That was thanks to Jitendra Malik, who became my advisor, joining Berkeley and teaching his first class. So it was a revelation. It's a bit like falling in love. I saw the possibility of working on images, which was a passion of mine. I really loved art. My mother had always taken me through art galleries and museums through Europe, and I had studied art history with passion. So I loved images. And I loved mathematics and engineering. And so all of a sudden, I saw you could put the two together. Images, which are a little bit fuzzy and soft, and mathematics, which is hard, and engineering, they could come together, and you could build a machine that could interpret images on a computational basis. So I thought, so if that could be done, that's what I want to do. As you may or may not know, at the time, we didn't know almost anything about even how to think about vision, not even how to solve the problems. So the questions we're asking were so elementary, and it had to do with image segmentation. How do you divide up the image into different areas depending on different colors and textures and stereoscopic depth and motion? But visual categorization, which became my obsession in the early 2000s, was certainly not even at the horizon. We didn't even know how to think about it. And so the reason why we had hope that one day it would work, well, it's because we have eyes and we see, and we know that we can deal with things in the world through our perception. And so if it works for humans, we should be able to reproduce these computations in a machine. That was the reason to have hope. Now, had we not had our own eyes and vision, imagine not being able to see, the idea that there are photons bouncing around the world and they hit things and finally they end up into your eyes, and now you know what is there in the world. It's crazy, right? It shouldn't work, but it works. And so we knew that that was a possibility. And the first place as engineers and mathematicians that we looked at was guidance from physics, from geometry. And so in the late 1900s, much of work in computer vision had to do with the physics of image formation and the geometry, and then trying to reverse the imaging process and recreate the 3D world that is outside from images. And so if you go through the proceedings of ECCV 2000, I remember at the time, I had started being interested in recognition, but the proceedings was 90% geometry, and there were maybe 2 papers in recognition, one of which was from my lab. It was completely different from today. And so at the time, I had thought that recognition was really a cool problem. There were so many people doing very good work in geometry. I didn't think I could add anything myself. And I was attracted by this fuzzy question: what does it mean to do recognition and categorization? And nowadays it's obvious to everyone. And so it feels almost like, how could you not know what it meant? But at the time, we didn't know what it meant. And so I was looking for ways to capture the question. If I look at an object like this object here that I have on my desk, is it a tape measure, or is it this particular Stanley Power Lock 16 feet tape measure, or is it an object, or is it a piece of hardware? What should I say? And then, how do I capture the fact that it moves? And so it was not clear, how many properties of the objects you would want to capture at once, and what is the definition of object, and at what level of abstraction you should try to classify objects. So all of that was fuzzy, and so people kept trying to formalize it, and it wasn't clear. And also, we didn't have any good data. We had very few data on which to carry out good experiments. So we had a data set on automobiles, and we had data sets of faces, and those were the 2 visual categorization tasks that were available. And so people working in visual categorization were obsessing about faces and automobiles because that's what was available. And any approach that you would see was handcrafted to do well on faces and automobiles, and it was not generalizing to anything else. My first student working on visual categorization was Fei-Fei Li, and so she and I had many discussions. At some point, I told her, Fei-Fei, we need to collect a more diverse set of data, and we need to have more categories, because otherwise we'll never be able to say that our algorithms are generally useful for categorization. We can only say that they are good for specific object categories. And so she said, well, okay, how many categories do we want? I said a lot. And she said, well, okay, so how about 10? And I say, no, 10 is not enough. And she looked at me, how about 15? Because it was difficult to collect images at the time. And so somehow it ticked me off that she was trying to do the minimum possible. I told her, okay, I want 100. Let's do 100, just like that. So she disappeared. She came back 2 months later with 101 categories, just to show to me that she had gone beyond what I had asked for. And that became Caltech 101.
How did you go about then collecting in these specific categories? Because it's not trivial to do, especially with a small team that you guys had. So you collected what was already available, or you created from scratch?
So at the time, the Google had started indexing images on the internet. And so we could type into the Google search box, we could say bonsai tree, and we get lots of images of bonsai trees. And then some student who was paid, some Caltech student, would download one by one the images, and some other student would clean up the collection of images to make sure that they were truly bonsai trees, because you could have the bonsai tree massage parlor or the bonsai tree hotel. And so you wanted to clean them up. And how did we come up with those 101 categories? So that's another good question. We had many discussions on how not to be biased by what we thought our algorithms could do. And so we had an idea of which algorithms would work. And so our idea was what we call the constellation model, so that objects in images are collections of texture patches that appear in a certain mutual position that is distinctive. And so think of our faces here in the video. You see 2 texture patches that are the eyes, a texture patch, which is the nose, the mouth. Well, you don't see my ears right now. And so the eyes are side by side, and they're above the nose, and the nose is above the mouth, and the mouth is above the line of the chin. So we thought that that was the right way to describe objects. But I told Fei-Fei, look, if we collect objects knowing what our algorithms can do, then we will only collect categories that fit our template. So we should really do an unbiased collection so that we challenge our own ideas. And so what we thought was, well, let's buy a dictionary, one of those that have pictures that are built for children that go to primary school. And so let's flip pages at random. And when we find a picture, well, that's a category we want to have. And so we went through this dictionary, and we selected maybe 150 categories from that.
Mm-hmm.
And for about 50 of them, we couldn't get enough images, but for 101, we could get at least 100 images, which was what we wanted, so that we could have 80 for training and 20 for testing. And nowadays, it makes you laugh to say, okay, you have a data set containing a little more than 10,000 images. Who would ever consider it as a serious data set? But at the time, there was nothing. And what we had done was, by the time standards, heroic that we had this data set. And in some way, it was the first well-annotated data set that was put out in this domain. And so it played a number of roles. And so this is important to say, what is the data set for? Well, it's for training and for testing. But actually, that was the more important side of it, was for defining what the task means. I said before, we didn't know initially what was the level of resolution at which you would want to categorize objects, and what does even an object mean, and is it okay if there is some background behind the object, or should it be on a blank background? And what about orientation? And so we said, no, you just download random images as people shoot them, and they are embedded in some background, and it's okay. Don't overthink it. Now, it's very important also to say that the field evolves, and so people realized soon that you could play tricks and recognize the categories without really recognizing the objects, because of the distinctive background, because the object is always in the same orientation, and then if you change orientation, it doesn't work. And that's okay. So each data set pushes the field in some direction for a while, and then it stops being useful because the challenge has been met. And now people have to think about what is it that we wanted to do when the data set is not really serving well. Maybe we thought it was good enough, but there are some ways in which it's not good enough. And so you move on and you collect another one. And so Fei then collected ImageNet, and ImageNet was pushing boundaries in terms of how many categories and how many images per categories you would want to have. And so it went from 10,000 to 1 million images and 1,000 categories with 1,000 examples each. And then we collected COCO, and COCO stopped being iconic. So the objects were not just in a picture almost by themselves, but now they were immersed in a context. And so all of a sudden, it was not image categorization any longer. It was detection and classification of specific categories. And so COCO had now 10,000 images per category to help people train on this much more difficult challenge, and so on. And so, you put out data sets, you try to explain what you're trying to do, and people work on it for a while. And then at some point, the field recognizes what are the limits of the data set, and somebody stands up and says, okay, I know how to push the field a little bit further. Here is the new data set, a new challenge, and you go on. So this is what happened.
Yeah, Pietro, do you think you mentioned earlier that at the beginning people were working on cars, and what was the other field again that you mentioned? Cars and faces, right? Yes. Yeah. And do you think your choices on how to build data sets and how to structure them, that this had for sure a big impact on what problems that researchers would work on down the line, right? Do you think this was more influencing the work of the researchers, your data sets that you were building, or down the line would it also go the other way, that the research was influencing how you build the data set?
So it was clear that we came in with these data sets at the right time. Okay, so I should say another piece of the story. When we published Caltech 101, we showed how we measured how well our algorithms are working on it, and it was 20% correct. So chance would be 1%, and we were 20% correct, which was 20 times better than chance. So fantastic, but certainly not 100%. And nowadays you laugh because it's, of course. And so the fact that we were doing, in quotes, so poorly on the data set, encourage other people to say, oh, let me try my own ideas. I'm sure I can do better than Pietro. And indeed, that happened. And so it was good that we published an interesting challenge. And so if you look at the number of papers on visual classification and visual recognition between ECCV 2000 and, say, CVPR 2005, you see a sea change. All of a sudden, boom, half of papers are about visual categorization, and people have enthusiastically embraced the challenge. And so I was surprised by how you can help a field grow by by putting out a challenge that is inspiring and clear and simple. And then, as you say, and as I was saying before, the more people worked on it, the more we realized that there were aspects of that specific data set that needed to be improved. And so, for example, Antonio Torralba had a nice demo in maybe 2005, 2006, where he showed that if you averaged all the images in each category of Caltech 101, you could still tell what object it was all about, because apples were all nicely centered and round and the same size, and so the average of all apple images looked like an apple. And so he said, you can just solve Caltech 101 by averaging the images and looking for nearest neighbor to the averages. And so it was not exactly true, but it was a very nice provocation that showed, okay, you've got to do something else to make it more challenging. And so that it pushed us forward. And so indeed, research will inspire new challenges, and it's a back and forth. Yes, absolutely.
Yeah, so basically working on the diversity of the data set, right? And making sure that the images are meaningful.
Yeah, so here is another thing I've learned that is useful. So in the early days of computer vision, there was no chance that we could have applications that were useful, or very, very little chance. Like a few things worked, but not many. And so you couldn't see many applications, and people were designing their own data sets and their own challenges. And it was a bit of an academic bubble, people talking to each other, and nothing works. As soon as you can, you should go out and apply what you think you know, because reality is out there. It's outside your lab, right? And reality bites. If you think you know how to do visual categorization, then tell your colleagues in biology, let me show you how I can classify your images of cells or your images of insects or whatever. And when you try, you fail, because you realize that there are some assumptions you're making in your little head in the lab that are not correct for the big bad world. And so the work you guys do, which is applying computer vision to real questions that people want to solve, is so important. And it's really important that you guys then turn around and explain to the field what is it that is not working, that should be working according to the papers you read, but it's not working in reality. And that you embody them in a data set that you give back to the AI community. And you say, look, this is our data set, and this is how current state-of-the-art algorithms are failing. And so it has to be a back and forth between practitioners and academics and theoreticians, if you will, where each one of us teaches the other side something that we've discovered that we know. That's very useful.
So you mean like a lot of back and forth between all the different parties that basically then led you to derive your principles on how to build data sets, right? So and there took a long time on building this out and building the principles there. When it comes to the modern approaches on how to algorithmically select data for data sets, to me comes to mind like taking clip embeddings of the objects and maximizing potentially those clip embeddings to ensure your data set is meaningful, it maximizes the feature space coverage of potential objects in the world, right? What do you think of such an approach, and where do you think this will be limited compared to, for example, heuristic approaches that you were mentioning?
Okay, so you mentioned a specific way to encode the appearance of objects like clip. And that has been wonderful, because it has shown to people that if you go multimodal, you can do a lot. So that's wonderful. Clip specifically, we all know has limitations. And so there is a paper that came out last year by one of my students, Rafi Khan, showing that clip is by construction unable to understand the association of attributes and objects, for example. And also clip has, it encodes the appearance of an object or a scene in a point in Euclidean space. And you feel like, okay, the point is a bit of a straitjacket. Like my objects could have many parts and attributes changing. And I could do many things that don't feel like just moving around in a Euclidean space. They feel like I need more, a richer set of primitives than just moving around in a Euclidean space. So we know that clip is really wonderful, and yet it has limits. The bigger question you're asking, which is what should we do now to grow and to represent appearances and so on? Nobody knows. And I'm looking forward to hearing from you guys. What are your use cases and which use cases are you not able to serve given the current representations we have? And so we'll start scratching our heads when we hear from you.
Yeah, I mean, I think that is the tough challenge here, right? Because we're hearing it constantly also from the customers and the potential customers. They don't know what type of objects they should choose to then train their text to 3D, image to 3D models, all those AI models, because they don't know like what they need to cover 100% yet. So that is a tough challenge, and trying to do this algorithmically for sure, like would be great for everyone involved, right? So maybe that is one of those first challenges to tackle on the research side, right?
I think maybe to add to this point, I think you mentioned it before. At some point, of course, with the best intentions and covering your bases as good as well as possible, by putting it out there, now all of a sudden you give researchers, companies, people who are interested, something to work with and leverage, right? At least if it's known and published by a well-respected institute or company. And I think already that is a great first step, and that is the first step towards this back and forth with the community in order to make both sides better. They will immediately discover limitations or also maybe things that work, and vice versa, and only that leads then to steady improvement over time.
And then you're getting back to exactly that thing that Pietro was mentioning earlier, so the constant feedback between practitioners and the researchers
100%.
or data providers in that sense, and then they will continuously make it better, right?
Yeah, and I have a specific question, maybe that's a bit more outside the research field, but now, of course, generative models have evolved in a fantastic way. I believe, and maybe you agree or disagree, happy to hear what you think about it, that, of course, models will get more specialized. People are getting more used to it. They want it to work even better, even faster all the time. And now we're all of a sudden getting into this exact same situation that you were mentioning before on the research side, right? People got used to it, and then they wanted more and covering more and more use cases. But of course, data in the image space, also in the 3D spaces, is by definition limited at some point, right? How do you think this will evolve, and what will researchers and companies do to keep evolving the models? Because it seems like there will be, or there is a glass ceiling, right? And that really hinders then output quality of some of these amazing AI models.
That's an interesting question. So first of all, for images and text, why is AI built on images and text? Well, because that's what we have very easily available, and we have plenty of it. And if you look at the sciences, there are some areas, for example, protein analysis and synthesis, that have made huge progress because these chemists had gotten organized ahead of time and had collected huge data sets of protein structures and proteins, right? And were running competitions already and so on. So where the data was already present and organized, people have been able to use AI techniques and adapt them to obtain amazing results, to the point that you may specify a function for a protein, and you may be quite lucky in being able to synthesize a protein that has that function, right? And so that's amazing. Now for 3D, the data sets are much more limited, and you guys are the heroes who are collecting the first data sets of a large varied number of objects. And so it's like a tiny grain of pepper in the middle of a sea, right? It's very small. So how can we do it? And so I can offer 2 or 3 thoughts here. So one is, I noticed that our algorithms, AI, wonderful as they are not efficient learners. And so I work a lot with large data sets of plants and animals. And so I invite the listeners to download the app iNaturalist and the app Merlin, Bird ID. iNaturalist can now recognize 100,000 different species of plants and animals. It takes an enormous number of training images for each new species that we put out. But a human expert, if they have to learn a new bird or a new plant, they just need to see 2 or 3 specimens, and then they are good to go, right? They may not be at the top of their skills, but they're already getting good. So clearly there is a gap of maybe a factor of 100 or 1,000 between the learning efficiency of a machine and learning efficiency of a human expert. And so it should be possible to, once you have enough examples of apples and pears, to then give the system a few pictures of melons and other round fruit, oranges, and so on. And the system should be good to go on the melons and oranges, right? But we don't have that technology yet. It's something that we need to develop. So that certainly has to happen. And a second thing that you guys are surely thinking about is using synthetic imagery. And so why not use our knowledge of how objects may distort and change in order to generate new versions of apples and potatoes once we have a few training examples. And that may also help because it embodies our knowledge. And so we should not forget that our visual system is very forgiving. So suppose that you had a penguin and you make its neck as long as the neck of an ostrich. You still see a penguin, and you see a penguin with a long neck, right? You say, I've never seen a penguin like that, but you recognize it. It's completely outside of a training set. And so there are these invariances or robustness tricks that the visual system can use, and we can composition between different experiences we have. And if a penguin is hanging upside down from a tree like a bat would, we still see a penguin, you don't see a bat. So there are so many things that our visual system knows how to do that our deep networks and transformers have yet to learn how to do. These generalization tricks. And so I'm sure that in the next 5 years, we will see a lot of that. My estimate is that there are 100,000 really smart people working on AI right now around the world. So
yeah, maybe even more, right?
Things will happen. Maybe even more by now, yes. Yeah.
And maybe staying on that train of thought, when you look at young researchers today, PhDs, and you have worked with so many, when you look at some areas that are evolving, where you say it's a smart way for a young researcher to dive deeper or focus their work on?
What should young people engage in? Is that the question? What should they think?
Not that broadly, but focused on
specifically in research.
In research.
In research in AI.
Yeah.
Okay, yeah, that's a $100 million question because, each one of us in academia, if you advise students, right now you face the following challenge. The students see their friends get highly paid jobs in industry and they want to leave their PhD and go to industry. And you are asking the students to work on problems, hopefully, where nobody else is working. So questions where there is no track record of anybody publishing. And so I remember when I started working in visual categorization, my students were saying, I don't want to work in this. Nobody's working on this problem. Everybody's working on geometry. I want to work on geometry. And I was telling them, look, if you work on a topic, it's a bit like investing in the stock market. If you invest in a company that nobody wants and 3 years later is on top, you've done the best you could possibly do. So it's the best time to invest is when nobody else has realized that there is potential there. And so you should develop good taste and you should understand what is really needed. And so to me, what I tell the students is, pick an area that speaks to you. And so think about the big problems of the world, climate change, pandemics, whatever is you think is really interesting, but also sports, whatever it is. And think what is missing and just think hard. Could AI do it? And if you say, no, I don't even know how to think about it, that's probably a good place to start. So people expect now everything to come out of the big tech companies. But it's not true because the big tech companies have to focus like laser beams on a couple of things that they can do really well and monetize. And so they're really spending most of their money in scaling. And there is an enormous space for academics and young people to invent new things that the big companies are not yet thinking about. So they should just pay attention to what is around you and see where there is a need and then try to work backwards. What would it take for AI to help in solving that need and try to have an original idea there. So I didn't give you a list of good problems, but I told you at the meta level, how should you think about coming up with a list of good problems?
Yeah, I think that's even better. I think you offer great advice on how they at least could think about focusing their time on. I think this has been fantastic, Pietro. I don't know, Burkhard, you want to add anything to that?
No, I mean, perfect advice, maybe for my kids now and for the next 5 years when they're embarking on that journey as well. But thanks for being here, Pietro.
Yeah, thanks.
Really appreciated it, and for sharing the amazing stories and advice for how to navigate that space. Right?
Yeah, thank you so much. It's been a privilege, Pietro. We hope to see you soon, of course, here in Italy, back in homeland at our company. But until then, all the best to you.
Always fun to talk to you guys, and I'll see you this summer, I'm sure.